So this problem is asking you to calculate the standard electromotive force for the following reaction over here. Okay, and this reaction is actually can be thought of as the two-half reaction, being that Fe2 plus. Okay, ignore the 3 from now. Fe2 plus 2 electron gives you Fe solid, but also Fe2 plus is also being oxidized, okay, to give you Fe3 plus aqueous plus electron. Okay, so we have a reduction and an oxidation, and the same species, Fe2 plus, is actually involved in both of them, and that can happen in a redox reaction as you're going from one Fe2 plus ion to another Fe2 plus ion. Now, I forgot to include this earlier, but if you look in your book, there's a table of reduction potentials, and it would be either in the unit, the current unit, the electrochemistry unit, or the appendix in the back of the book, depending on what book you're using, depending on what book the class is using. Okay, and so I found these two reduction potentials, one for the reduction of Fe2 plus to Fe, and that is this one, and the reduction of Fe3 plus to Fe2 plus with this reduction potential. So in the equation as it's written, the reduction that's actually occurring is this one. So I'm going to highlight this with the same color. Okay, we're going to show that this is the reduction potential for this equation. Okay, here is this, and then this one is being reduced. So we're going to go ahead and go with this reduction potential. Okay, however, the other substance, Fe2 plus going to Fe3 plus, that's an oxidation equation, and we have the reduction potential up here. Okay, so what we do is we can flip this equation around, and we can give that an oxidation potential instead. So what I'm going to do is I'm going to flip this equation, and let's do it over here, to say Fe2 plus aqueous goes to Fe3 plus aqueous plus E negative. And the oxidation potential then means that you switch the sign and you make it negative 0.77. And I'm going to go and cross this off. Okay, and you can see how the equation actually added up to give you this overall equation right here. Okay, if I want to get the electron to cancel, because this indicates that 2 electrons were transferred, whereas this one indicated only 1 electron was transferred. So if I multiply this line by 2, and we get 2 Fe2 plus, 2 Fe3 plus, 2 electron, you can see that the electrons here would cancel. And then if you add up the Fe2 pluses and 2 Fe2 plus, you get 3 Fe2 plus. This is where the Fe solid comes from, and that's where the 2 Fe3 plus comes from. So the energy potential of the cell, the electromotive force, is actually the equation we're going to use. It's called the E reduction plus the E oxidation potential. So in that case, that's going to be negative 0.44 plus negative 0.77. And that's going to give you a voltage of negative 1.21 volts. Okay, also, this is very important for you to note that reduction and oxidation potential do not depend on the number of moles of electrons. So even if you were to multiply this line by 2, you do not multiply this by 2. Okay, so same with this one. If you multiply this line by, say, 3, that does not affect the reduction potential. Okay, with delta H, with Hess's law, we had to multiply the delta H because that was on a per mole basis, whereas reduction potentials are not on a per mole basis. Okay, this problem is slightly different. this point is giving you two different reduction potentials and two half reactions, and it's asking which one to write a cell reaction that would occur, meaning thermodynamically favorable, and calculate the electromotive force of that cell. So when you look at these two reactions, we can see that the reduction potential is this one is negative 0.858 voltage and the other one is negative 0.43 voltage. So the one that has a higher reduction potential is the one that is more likely to occur in a thermodynamically favorable galvanic cell. Okay, so in this case, we're going to mean that this is the equation right here that's going to occur as the reduction. I'm going to put a star next to it, which means the first reaction is the one that's going to occur as an oxidation. So I'm going to go ahead and flip that first equation around. Okay, so AU solid plus 4Br negative will yield AU Br4 negative aqueous plus 3 electron. And that reduction potential no longer applies because it is now an oxidation potential of positive 0.858 voltage. I'm going to cross off this line. And now we want to get the electron to cancel. So I'm going to multiply this equation by 3 and put a 3 here. And that means that your electron, you can now cross them off on this side and this side to give you an overall equation of AU solid plus 4Br minus AQ yield AU Br4 minus AQ plus 3EU2 plus AQ. And I also should have added over here, sorry about that, 3EU, 3 positive. Okay, and again, because we multiplied this line by 3, that has no impact on the value for the reduction potential. So the oxidation plus the reduction potential will give you the overall E for the cell. Okay, and we're going to take the positive 0.858 voltage minus 0.43 voltage, and that's going to give you 0.428 the electromotive force for that particular cell. Okay, so we're going to be talking in a moment about what the sign of the electromotive force tells you, but this is how you would write the reaction that would occur for a thermodynamically favorable cell. Now remember, don't assume that you always take the lower reduction potential and make it positive or change the sign of that. It really depends on what information is given to you, whether we tell you it's a galvanic cell or electrolytic cell, what equation we give you, etc. So just bear that in mind as you complete the homework and the pretest.